Hey, Benjamin. All right, it's 4 o'clock, so let's go ahead and get started today. All right, good afternoon, everyone. How's everyone feeling today? How's everyone's weekend?
We're good. How are you, Professor?
Good, good. Yeah, it's I need a haircut, so I'm getting a haircut this weekend. But my
You
long
look
hair
great.
is thank you. But it's starting to bother me because it's tickling my ears.
Ah,
But yeah, that'll be for that. But I guess today we can be peak ANSYS usage for 2 more days. Okay, so today the plan is we're going to go over a new set of lecture notes on 3D elements. And so this is kind of continuing our series on different element types. And so last week before the ANSYS activity, we did 2D elements. And so now we're going to complete it with 3D. Okay. And so with this, then you'll have kind of not everything there is to know because, element types go pretty deep. But at least enough to really understand the options that are available to you in ANSYS. Okay. Another announcement. So I've already looked at all of your project proposals and I've given you feedback on them. And so I wanted to make sure I got you guys feedback on that as soon as possible, just because we are kind of winding down on the semester, and so I want to make sure that you guys have my feedback before you really get started working on that. So please check that if you haven't already. And they all look great, and so I was really happy with all the proposals. And so I'm really excited to see what all of what all of you end up doing or what all your simulation results end up looking like for your projects. And so I think everyone basically said this sounds great, but I just had some ways to suggest some modifications or some other things that you can consider. Okay. Um, yeah. So today we're doing notes. And so for a lot of you, if you read my feedback, then I'll either give you some advice or some things where I might tell you this is where I might see some pain points, or I might have given you some suggestions about maybe you can consider this. So and so don't I want to tell you, don't take those things, don't take those suggestions as kind of like I'm telling you to do those things. Those are just kind of some things that I thought of in the moment that might be interesting to look at. But end of the day, it's your projects, and I think all of you are doing something that I think you kind of understand the background for the project a lot better than I do, especially the ones that are doing this for like maybe like for a school project, like for Baja or for Formula or for Aero, or if you're doing this for your senior design, like you guys know those projects, and you guys know what you're looking for a lot better than me. And so the suggestions that I take, don't take them, don't say that, oh, I have to do these things. Those are just, some things that I might think are interesting, but they're not binding at all. So I guarantee you that, when you go to turn in your reports, I'm not going to remember what I told you in the proposal. So, you don't have to worry about like, I'm going to check specifically for these things. Okay. I mean, you still have to satisfy the basic requirements for the project. And so, those are outlined, all of those in the project specs. But anything additional that I mentioned to you in the feedback, that's not binding. And so it's not like I'm going to go check on that later. And so you guys are the project experts on this one, and so I want you guys to kind of drive. I really want you to use this project as a chance to use ANSYS to find something that you're interested in, or something that will be helpful for you for your projects. Okay. um, all right. Let's see. Homework. The next homework is due on this Friday, and so that's the strong form, weak form, finite element forms homework. And so that's a big one. And so I know there's a lot to do in that homework assignment. But the midterm, which is going to be in 2 weeks, is going to mimic that very, very closely. Right? And so if you understand that homework and you can do all the problems really well, you're going to be in great shape for the midterm. Okay. All right. So any questions? Are there any questions I can answer before we get started today? Okay. All right. So let's go ahead and get started. And the topic for today's notes is going to be 3D element types. All right. Okay. And so we've, just like I mentioned before, we've finished talking about 2D element types at this point, which are great. So I think 2D, going over the 2D elements is good for talking about just some general properties. But in reality, we live in a three-dimensional world. We're all three-dimensional boys, girls, and non-binary. Whatever you identify as, right? And so we live in a 3D world. And so usually for most practical applications, you're going to be using 3D element types just because you have 3D geometries, right? And so it's only fitting that we talk about these and talk about what your options are for finite element analysis, and what should go into your decision-making process when you choose which elements to use. Okay. All right, and so there's two main shapes for 3D elements. So in theory, you can have any shape that you want, but practically speaking, there's we stick to the ones that kind of work the best. Okay. And they're you can almost think of them as like 3-dimensional versions of our 2D element types, right? And so the first shape is a tetrahedron. Okay. And so a tetrahedron is nothing more than just a 4-sided pyramid. Okay. And so schematically it looks like this, right? So it's a pyramid with just 4 sides on it. So a triangle, it's basically every side of the pyramid is a triangle. Okay. And the other type of element that's used most often in 3D is a hexahedron, or what I like to call this more as it's a brick element. Right? And a brick is nothing more than just a 6-sided box. And so those are the two main, elements that we have. And, we've all kind of seen this at this point because, we've done so many ANSYS activities up till now. And we've already seen that, when you do meshing, you can either do a tetrahedron or a hexahedron, right? So, this is not new information. But what I want to talk about today is, how, what are the properties between these two elements, when you should use one or the other one, and also talk about their linear and quadratic versions, right? And so it's, this is very much going to mimic our lecture notes on 2D elements. Okay? And what I want you guys to keep in mind as we're going through this is that the tetrahedron shares a lot of the same properties as the 2D triangle. Okay? Right. And so basically everything that you understand for the triangle, it's going to apply to the tetrahedron as well. And the hexahedron is very similar to the 2D quadrilateral. All right. Okay. And so if you kind of understand that, then you've kind of already seen this lecture today. But let's go over each of the shapes in general. Okay. So let's start with the linear tetrahedral. And remember, the reason we call it linear is because the shape functions for this element is a linear function. And so I'm for these, because there's so many nodes here, and you'll see even more, once we get to the quadratic hex. I'm not going to write out all the separate shape functions, but I will give you kind of the generic form of the interpolating polynomial, right? Just so you can kind of see, what the functions look like. All right, and so since now we're in 3D, we have all 3 spatial dimensions. So we have x, y, and z. And so the interpolating polynomial has 4 terms for this. And so we have our constant term, C0. We have our term that's linear in x, C1x. We have our term that's linear in y, C2y. And our term that's linear in z, C3z. Okay. And so if you're talking about just 3-dimensional functions that have x, y, and z, this is basically as simple as you can get, right? And so we have basically everything is kind of a true linear. Right? And there's four, and notice that there's four constants here because we have four nodes for a tetrahedral. All right. And so, we can go through the same exercise as what we usually do for these elements where, if we require that this interpolating polynomial matches the solution values at each of the nodes, we can use that information to solve for each of these constants, right? And then from those constants, we can put this in terms of the four shape functions and, away we go from that. But, just because just because that exercise, we've kind of done that before, several times at this point. And for 3D, it just ends up being more tedious than helpful. I'll let you kind of imagine what that looks like. Okay. All right. So any questions on this so far? Okay. All right. And so what are some of the properties of the tetrahedron? And so the first property I want to talk about is the simplex property. Right? If you remember, what the simplex property means is that you can use a tetrahedra to fill basically any 2D, any 3D volume, okay? Regardless of how complex or how weird that geometry is. Okay? Okay. And this is really nice because, a lot of times in finite elements, you're not working with the simplest geometries. You're working with kind of realistic parts and realistic, geometries. And a lot of times those are pretty complex. And so tetrahedrons, is always going to be guaranteed to give you some kind of mesh, right? And that's a very valuable property. It might not be the most efficient mesh, but you will get a mesh, right? Which is very underrated, and so it's a very nice thing. Right? And so just to kind of give you guys an example, so a lot of my own research, I do finite element simulations of blood flow in the human body, right? And so the human body doesn't care about your finite element analysis at all, and so your blood vessels are just going to take kind of any shape that's convenient for them. And so you end up with a lot of kind of loopy, complex structures there. And so for my own work, the only element that I actually use are tetrahedra, because if I try to use, other element types, then it's meshing that is just going to be a huge nightmare. And so this property, it might not seem that impressive, but it's a really, really valuable property. And so, I think overall, it's hard to say because I'm not familiar with all aspects of finite elements, but I would hazard a guess that tetrahedra are used probably most often. It's probably the most often used finite element type, just because it has this nice property of being a simplex. Okay. Right. And so when you're coming across a new finite element problem, and this goes for all your projects too, starting out with the tetrahedral mesh is usually a really good place to start. And this is especially true, for if you're working with an assembly with lots and lots of different parts. Okay. Because for sure that if you use tetrahedrons on your complex assembly, you're going to get some kind of mesh out of it, which is good, right? And then from there, you can add things like refinement, maybe change some part to a hexahedron mesh, and then kind of go from there, right? Because the nightmare scenario that people end up having to face, in practice is that you have this very complex CAD a very complex assembly, and you try to kind of mesh everything, beforehand. And so you try to, put in your complex meshing setting, you put hexahedrons on there, and then it all just fails. And then you're stuck kind of trying to figure out where exactly is the mesh failing to mesh. But if you start with the tetrahedral mesh kind of all the way around, and then kind of modify things kind of step by step, then that's usually a much more systematic and a lot more practical process to go about it. Okay. But what are some of the downsides to this? And so just like kind of their triangular cousin, tetrahedra suffer from this fact that they don't make very efficient meshes. Okay? And so even though they can fill any kind of 3D space, it's usually going to take them a lot of elements to fill that space. Okay? And so if you do end up doing a tetrahedral mesh for your entire assembly, you might end up with the mesh with just a bajillion elements, and it becomes a little bit too much for your computer to handle. Okay. Another drawback specifically for linear tetrahedra is that they're very susceptible to shear locking. And so if you remember, what shear locking was. Shear locking was what happens when you try to run a structural simulation with linear finite elements, and the structure kind of locks in on itself, and then you end up with displacements that are not that are much lower than what they actually are. Okay. And so linear tetrahedron, because of its shape and also because of its shape functions, makes it kind of especially susceptible to this. Okay. And so if you want linear tetrahedra to work for your problem, you really need to be careful with the refinement. Okay. Or in other words, you really need to make sure that you really refine in the areas where you think there's going to be some a lot of interesting behavior. Okay. Okay. Right, and this is especially true for structural problems, because not only do you have the shear locking stuff, but getting an accurate result with tetrahedrons, you really have to refine it a lot. Okay, but I will say that if you're working with either a thermal problem or a fluids problem, I don't think anyone's doing a fluids this year. But for thermal and fluids problems, linear tetrahedrons are actually a pretty good choice for that because they don't have that shear locking problem. Right? And so, like in my own work, I've used mainly just linear tetrahedron just because it's mathematically it's the simplest to deal with, and you can fix most problems by refining, and that's usually an easier route to go than trying to implement quadratic tetrahedron. Right? But that's a problem that's really unique to just writing your own code for these things. Okay, so any questions on this so far? Okay, all right. So that's the linear tetrahedra, and so now let's talk about the quadratic tetrahedra. And so the shape of the quadratic tetrahedra looks the same. It's just that we're going to add some additional mid nodes here in order to have a quadratic function. Okay, And so in total, you know, if you draw a node on each side of the triangle or each edge, you're going to end up with 10 nodes overall. Okay. And so it's a big increase. So, you know, our linear tetrahedra had 4 nodes, and now our quadratic one has 10. Okay. And so here is our tetrahedron, and of course we have all of the end nodes here. Okay. In addition to the end nodes, you know, we have to add nodes at each of the middles of the edges. And so if we number these, you can see we have 1, 2, 3, 4. And then for the mid nodes, we'll say this is 5, 6, 7, 8, 9, 10. Okay. All right, so 10 nodes overall. And so if we write out the interpolating polynomial for this, you'll see that we have all of our linear terms in addition to all of the quadratic terms as well. Right? So t of x, y, z is equal to c0 plus c1x plus c2y plus c3z plus c4x squared plus c5y squared plus c6 z squared plus c7 xy plus c8 xz plus c9 yz. Okay. And so, you know, you can see here why, you know, I'm not writing down all of the shape functions, because here we'd have 10 different shape functions to look at, right? And so that's kind of a little bit too much for something like this. And so, you know, just be aware that, you know, just know that, you know, for quadratic tetrahedron, we have 10 nodes, and thus we have 10 shape functions. And remember, the way that we obtain these shape functions is by solving for each of the constants here in this polynomial. Okay. All right. And so for the quadratic tetrahedron, you know, there's not really much more to say, just because, you know, we've said a lot about, you know, linear tetrahedron and quadratic triangles a lot. But let me just kind of write down some stuff just to just for completeness. Okay. And so just like its linear cousin, you know, the quadratic tetrahedron has the simplex property. Which makes sense because it's still a tetrahedron, okay? And so it can mesh any kind of 3D geometry, which is great. Okay. And because of its quadratic nature, and you know, because it has quadratic shape functions, you avoid the situation that causes shear locking, right? Because remember, shear locking happens because you know, when you compute the stresses within the element, for a linear element, you end up getting a constant stress element. But because we have all of these quadratic terms here, okay, not only just in the, you know, obviously we have x squared, y squared, z squared, we also have all these cross terms as well, right? And so because we have all those cross terms, you know, your stress can actually vary within the element, and so you're not as susceptible to shear locking. Okay. All right, so that's nice. And so, you know, quadratic tetrahedron, yes, you pay a little bit more per element, and it makes your simulation a bit more expensive. But that pay is usually worth it, because you end up with something that's, you know, more stable and more accurate. And you usually don't have to refine your mesh nearly as much for quadratic tetrahedron. Okay. And besides that, you know, besides the difference between, you know, the shear locking, the quadratic tetrahedron shares a lot of the same properties as the linear one. And so, you know, there's not really much more to say kind of beyond this. Okay. All right, so any questions on the quadratic tetrahedron? Okay. All right, so that's it for the tetrahedron. And so now let's go over the brick elements, right? And so now let's go over the linear brick, or the linear hexahedron. Okay. And so this is kind of the other common element type that's used in 3D FEA. Okay? And so the linear tetrahedron, hexahedron has 8 nodes, okay? One for each of the vertices on the brick. Okay. Okay. And so here is our brick. And so I drew it like a cube, but it doesn't have to be a cube. And so each of the sides can be different lengths. Okay. And oftentimes they are, and that's actually one of the benefits of the brick element. Okay. Right. So we have 8 different nodes here. And so just like we've done for the tetrahedrons, let's write out the interpolating polynomial. Right. And so this one's going to have 8 constants because we have 8 nodes here. Okay. And so we have C0 plus C1x plus C2y plus C3z plus C4xy plus C5 xz plus C6 yz plus C7 xyz. All right. And so, this is our linear interpolating polynomial. And, just like we saw for the quadrilateral, we have all of these cross terms here, okay, which might not look like a linear term, but, we can kind of think of them as like pseudo-linear. And the reason for that is because, they don't have any x squared, y squared, or z squares on them. Okay. All right. And so unlike the tetrahedron, the hexahedrons here don't have that simplex property, right? And so it's very possible to end up with failed meshes with hexahedrons. Okay? Right. And a lot of you have kind of experienced this firsthand already. And so for activity 2, remember that was our activity on the bike crank. A lot of you, when you tried to mesh this with hexahedrons, answers kept coming back to you with errors, right? And so the reason for that is because it just wasn't able to fit into a curve. It wasn't able to fit these kind of box elements into that curved geometry. Okay. And so, if you had that problem, you've experienced it, but if you didn't, then it's okay. You might be wondering, why did some people have issues with the hexahedral mesh, but some people didn't? And it's a good question. And the reason for that is because there's some meshing is not an exact process, and so every time each computer will usually mesh something a little bit differently. Because the way that meshing typically works is that you take your CAD geometry and it finds where all the solid parts are, and it kind of semi-randomly puts points. It starts by kind of populating your geometry with a bunch of little points, and then it tries to connect them together into an element. And so because there's that little bit of randomness, every computer does kind of random a little bit different way. And so there's some computers that you might get a meshing error with it, but another computer might be perfectly fine. And so it's kind of the annoying thing with finite elements, just because of that kind of random aspect into it. But it's also good sometimes too, because if your meshing isn't working on one computer, you could try it on someone else's computer, and see if that works. And then once you get the mesh for that one, you just export that into your model. And so I'm speaking from experience, and so it's happened to me quite a bit. throughout my research life, that a lot of times I would my mesh would fail on one computer, but it would work on my friend's, and so I'd make him do it, and then I just get the mesh from him after that. Okay. But what are the and so now what are the benefits of using hexahedra over tetrahedron? Right? And so the benefits for using hexahedron is that it can end up with a much more efficient mesh for certain kinds of geometries. Okay. And those geometries are ones that are kind of what I call like box-like. Okay. Okay. Or in other words, geometries that have a lot of straight, straight faces and sharp corners. Okay. Because if the geometry already has, these kinds of features, they have kind of flat surfaces and sharp corners, then you can imagine that putting a hexahedron in there or putting a brick is kind of just a very, very natural thing. Okay. And so on the next page, I'll kind of show you kind of an example of what I kind of mean by this. Okay. So are there any questions on this so far?
Could you just go back one page real quick?
Sure.
Thank you.
Okay. And so let's go ahead and draw what some geometries would work well for hexahedrons and what kinds of geometries wouldn't be. Oh, question. Oh.
Wait, can you go back one? Oh, thank you.
Yeah. All right, cool. All right, so on the left here, I'm going to draw a geometry that's very box-like, right? Which would work for a hexahedron. Okay. Okay. So it's not the most exciting example, and you probably won't have something like this in practice, but this is kind of the extreme case where a hexahedron would work really well, right? And so you basically just have a long rectangle, right? And so you can imagine it, you can basically fill this together with hexahedron just like this. Okay. And so this is very box-like because it has sharp corners and straight faces. Okay. And so the opposite of this, where hexahedron wouldn't work, would be something with a lot of curved edges, right? And so kind of the most extreme case for this would be a sphere, right? And so a sphere is something is kind of the quintessential, curved like surface, which doesn't have, any kind of sharp corners or any corners at all, right? Because it's a sphere. And so something like this, a hexahedron would probably really struggle to mesh on this. And so for something like this, you'd have to mesh it with hexahedrons or tetrahedrons, sorry. Okay. All right, question. So what about hexaminate meth that uses both hexahedrons and tetrahedrons where the hexahedrons can't be formed? Yeah, so that is, and so I know ANSYS does have that feature where they said, I think the setting is, it is called hex dominant. And so I'm actually not sure exactly how they, how they determine that. And so how they determine, which areas, are going to use hexes and which are going to use tets. But ideally, yes. So ideally, that would be the most efficient thing to do. Whereas if you can put a hex in there, put a hex because it's going to be a lot more efficient. And then for the places where it can't, just go ahead and fill that spaces with tets. And so that's kind of the most ideal thing. And I know ANSYS has an automatic setting for that. I'm just not 100% sure how it works, and I've seen it kind of fail in a lot of cases as well. And so sometimes you just kind of have to force it to go to TETS for cases where it fails. Yeah. How I think it might work is that it might look at your CAD geometry kind of beforehand and kind of measure the places where it can measure some curvature, and then based on that local curvature, it might try to fit some TETS in there. But sometimes that's not a perfect thing as well, and so sometimes that still might fail. Yeah. Mm-hmm. All right. And so if you let's talk a little bit about why hexes are more kind of efficient. And so I think we kind of mentioned this before with the quadrilaterals as well, but I don't think we went too much into detail about it, right? And so one thing I can show you is I can basically just take the same example up here, and then let's say let's take this rectangle and let's mesh it with TETS, right? We're going to be using triangle because it's a 2D, but you can imagine it's kind of the same thing. Right. And so if we were to mesh this geometry with TETS, it probably looks something like this. And so you would basically just take, each of the hexes that were there before, and then just split it in two for TETS. Okay, because remember the TETS are, they're basically triangular structures. Okay, and so in this kind of, this toy kind of situation here, you end up with literally twice as many elements to fill the exact same space with those elements. Okay. Okay, and so that's one reason. So just by the nature of a hex, just naturally by itself, kind of taking up twice as much space as a TET, you can fill a space a lot more efficiently with a hex that way. Okay. Another reason for for hexes being more efficient is that they're a lot more flexible in terms of its aspect ratio. And so what do I mean by aspect ratio? All right, question. So when we talk about 2D element types, would that relate to the first ANSYS activity, and then 3D element types would go with the CAD models we've been working with recently? Yep, that's correct. And so our first ANSYS activity, we did 2D elements with that, and then everything since then we've been doing 3D element types. Yeah. Mm-hmm. Right. And so, what do I mean by aspect ratio? So aspect ratio is kind of the ratio between, the longest and the shortest dimension of a shape. Okay. Okay. And so, if we have a, let me give you some examples. I think it's kind of easier just to kind of show some examples here, right? And so if we have a square here, and we look at this dimension L versus this dimension H, right? The aspect ratio would just be the ratio of L to H or H to L, whichever one works, right? And so for this case where we have basically a square and L and H are approximately the same, we say that the aspect ratio of this shape here is approximately 1. Okay? Okay. And ideally, when you're doing finite elements, ideally when you mesh your geometry, most of your elements should have an aspect ratio of about 1, right? And so what that basically tells you is that your elements are better quality. Okay, and so one way to say is that good quality elements good quality elements have an aspect ratio of about 1. Okay, and so that basically tells you that all of your elements, they have roughly the same size, and they have roughly the same shape, and none of the elements are really getting distorted. Okay, and so practically speaking, it's impossible to get a mesh with aspect ratio 1 all the way around, just because you have to fit the elements into certain corners. But typically, a good meshing program will basically make it so that most of your elements are around this quality here, right? Because otherwise, if you have poor aspect ratios, then that leads to some numerical difficulties. Right? But hexes actually have this benefit where you can modify the aspect ratio, and you can have elements that look really kind of squished, and you can actually still end up with some pretty good results. Right? And so let me kind of show you what I mean by that on the next page. And I'll show you why tetrahedrons can't do this, and that's kind of a big reason why tets are not as efficient as hexes. Okay. All right, so before I do that, are there any questions on this? Okay. All right. And so when I say hexahedrons are more flexible with their aspect ratio, that means we can have distorted hexahedrons and still end up with a good quality mesh. Okay. And in particular, the thing that hexahedron can do really well compared to tetrahedrons is that they can become squished, right? And so, you're not limited to hexahedrons that look kind of like a square like that. And so you can have hexahedrons that look kind of like this. Okay. And so this is fine actually. And so, even you can have a very long skinny element like this with obviously a very large aspect ratio, but your simulation is actually still going to be okay, right? And so long, skinny, still okay. Okay. But the same isn't true for tetrahedrons, right? And so for a tetrahedron, you can't really stretch it out all that much and still end up with a good simulation, right? And so I'm going to draw 2D shapes here just because it's a little bit simpler. But let me show you what happens when you stretch a triangle by a lot, right? Okay. And so that's not a very good image actually. So let me kind of draw it a little bit better. Okay. All right. And so not okay. Right. Because look what's happening here at the on the right side of this triangle, right? And so on the right side of this triangle, you can see that because we're kind of forced into this kind of triangular shape, we have those two edges come very, very close to each other. Okay. And so these are usually things that are not very good for your mesh, because to get into kind of the reason why would take kind of a long explanation, but basically what you can think of is that because of the way the shape functions of the tetrahedron are, if you have kind of an area of your element like this, then it ends up really deteriorating the accuracy of your results, right? And so what usually ends up happening if you have a long skinny geometry tetrahedrons really struggle in these, you know, in these cases. Yeah. Question. So essentially, no sharp edges for hex. And so this doesn't really have anything to do with sharp edges. It's more just kind of the aspect ratio for the elements. Yeah. And so if you have kind of a long, skinny geometry like this, you know, what you can do for the hexes is that you can do something like this. And so you can have these layers of like really long, skinny elements like this, you know, and still be relatively okay, right? It's not, and I'll say this is not ideal. And so, you know, for actually, you know, for these situations, there is something better that you can do, which we'll do in activity 5. But, you know, you can do this and it'll still be okay, right? And so if you try to mesh the same geometry with tets, you know, you're going to end up with something like this, right? You might have your layers like this, like just like before, but in order to make sure that the aspect ratios of the tets don't stray too far from 1, you know, you might end up with like a mesh that looks like this. Okay, and so you might end up with just a lot of tets in that space, you know, to try to fill that space, because each of the individual tets can't be stretched and can't be distorted like the hexes can. Okay. Okay. And so I'm just drawing kind of a quick image here, but you can kind of imagine that, you know, instead of having a few long, you know, skinny elements that fill that space, you instead have to have, you know, a lot of tets that all kind of have to look like the same, and then kind of has to fill that entire space. Because tetrahedrons just naturally, they really don't like to have their aspect ratio stretched from 1 too much at all. Okay. Right. And so you can see from here that, you know, because hexahedrons are much more flexible with their aspect ratio, you know, for cases where they work, you know, they can mesh those kinds of geometries a lot more efficiently. Okay. And mesh quality is something that you can check as well. And so I'm actually not too sure how to do it in ANSYS. I think, you know, I'd have to look that up, and maybe we can check that for the next activity. But checking the mesh quality is something that's really important for finite element analysis as well, right? And one of the things that they check for mesh quality is aspect ratio, right? And so, you know, it's not the only thing that they check, because there's other things that to check for mesh quality, but it's one of the big indicators that they look at. Okay? But ANSYS is pretty good, and so, you know, ANSYS mesher is usually, you know, if it meshes, it usually ends up with a really good quality mesh, at least from everything that I've seen. And if it can't produce a good quality mesh, it just gives you an error, which might seem frustrating, but that's actually sometimes more helpful than it giving you just a really poor quality mesh. Yeah. All right. So any questions on this before we move on to the quadratic hexahedra? Okay. All right. And so the quadratic hexahedra, and so this one's kind of a monster, and so you can almost think of this as you know, per element, you know, if you count up all the corner vertices on a box and you put a vertice on the middle of each of the edges, you know, you'll end up with 20 nodes per element. Okay. Okay. And so with 20 nodes per element, it might take us, you know, a good 45 minutes to write out all the shape functions, and so we're not going to do that. And so let me at least, you know, draw you the shape just so you can see what it looks like. Right, so just like before, we have all of the corner nodes, and so we have 1, 2, 3, 4, 5, 6, 7, 8. Right, and in addition to that, we have all of the mid nodes. Okay, and so basically, in the middle of every edge here, we have to add another node. And so let's see, where do I start counting? Let's see, so we have 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Good, so I got all of them, okay? All right, so it's a lot, it's a lot of nodes, and you know, it's a lot to take into account. Okay? And of course, the interpolating polynomial here will also have 20 different terms in them, right? And so let's go ahead and write down all of them just so you can see what the function looks like. Right, so first we have C0 plus C1x plus C2y plus C3z plus C4x squared plus C5y squared plus C6z squared, right? Then we have all the first order cross terms, and so we have C7xy plus C8xz plus C9yz, okay, plus C10 x squared y plus C11 x squared z plus C12 y squared x plus C13 y squared z plus C14 z squared x plus C15 z squared y plus C16 xyz. Then we finally have the xyz terms with the quadratics, right? So we have C17 x squared yz plus C18 xy squared z plus C19 xyz squared. Right. So it's a doozy, and so it's a lot of different terms here, right? And so as you can imagine, you know, figuring out the 20 shape functions from this guy is not an easy or pleasant task, and so it's even I haven't seen what all the shape functions look like for the quadratic hex, just because it's 20 of them, and you know, nobody really has time for that except for the really hardcore finite element people. Okay, and so, you know, at least in terms of this class, this is kind of the cream of the crop that you can use, right? And so in terms of a per element basis, you know, this is going to have the highest cost, but also gives you the highest return, right? And so you can almost think of this as kind of like the Rolls Royce or the Louis Vuitton, or, you know, the Whole Foods of finite elements, right? And so, you know, very premium, but, you know, you get what you pay for. Okay. Okay. And so, you know, fortunately, you know, now that we've reached this point, you know, there's not really much more to say about the quadratic hex, and because at this point, you know, we've gone over, you know, quadratic elements quite a bit. We know that, you know, this is going to do better with shear locking, and we also know that because it's a hex, it has very flexible aspect ratio properties as well. Okay, and so there's really kind of not much more to say, and so, you know, I'll kind of leave it with this, and then, you know, next I want to talk about, you know, how do you actually go and choose, you know, what type of element and what type of order do you pick for your element? Okay. Okay. So any questions on this so far? Okay. All right. So the next section I want to talk about is, you know, how do you choose an element type and element order? Okay. And so, you know, at this point, you know, we've gone over all of the 2D and 3D element types, or at least, you know, the main ones that you have access to within ANSYS, right? And so we've gone over triangles, tetrahedrons, and quadrilaterals and hexahedrons. Okay. And so they share a lot of properties. And so, you know, what I thought would be useful was to, you know, make a table for you guys to kind of help you with kind of the decision-making process for, you know, which element to choose. Okay. And so this table is going to have 4 different quadrants. And so on one side, I'm going to have the element shapes. Okay. And so let's on the one hand, we'll have triangles and tetrahedrons over here. Okay. And then on the bottom here, we'll have quads and hexahedrons. Okay. Right. And then over here, we'll have 2 different columns. So one column for linear elements and another column for quadratic elements. Right. Right. And so, in this top left here, you'd have linear tetrahedrons or linear triangles. And in the top right, you have quadratic tetrahedrons or quadratic triangles. And then the same thing for the hexahedrons. Okay. And so in each of these different spaces, I'm going to tell you basically kind of the pros and cons of using these types of elements. All right, so let's start in the top left. Right? Actually, let's kind of build this kind of point by point. Right? All right, and so for both linear tetrahedrons and triangles and quadratic tetrahedrons and triangles, they have the simplex property. And so that goes for both of those. Remember, the simplex property is the property where they can be used to mesh any geometry out there, right? And so if no matter how complicated of a geometry that you have, tetrahedrons will do the job for you. Okay. And so that's a nice thing. And so if you choose triangles or you choose tetrahedrons, you're guaranteed to get some kind of mesh. The downside to that is that, it might be able to mesh any geometry, but it might not do it in the most efficient way possible. Right? And so this leads to sometimes some inefficient meshes. Okay. And by inefficient, what I mean by that is, the mesh is going to require more elements than normal. Okay. And the main reason for this, as we talked about before, is just, it's just kind of a natural consequence of how these shapes are shaped. Okay. And because of their shape, they can't really be distorted too much. And so they really like to have their aspect ratio around 1. Okay. Okay. And so the next point is, we're going to have a difference between, between linear and quadratic, and that for linear elements, remember, we have this thing called shear locking. Right. And so that's a big weakness of the linear tets. Okay. But it's a good thing for quadratics, because quadratics, you don't really have to worry about shear locking. Right. And so that's a plus right there. Okay. All right, and so where would you want to use this? And so for linear tets, this is great for thermal and fluids. Okay. Okay. And so it's great for that, but not so great for structures because we have that shear locking phenomenon. Okay. And so for quadratic tets, this is usually good for thermal fluids and structures. Okay. And so those are some applications where you would use it. Okay. All right, and then finally, let's kind of remind ourselves how many nodes do we have per element, right? And so for the linear tets, we have 4 nodes per element. Okay. And then for the quadratic one, we have a big kind of increase in cost per element. And so we have 10 nodes per element. Okay. And so remember, whenever we go up, whenever we change from linear to quadratic, per element, the cost is going to increase. Okay. So that's something that's important to remember. Okay. Okay. So that's everything for the tetrahedrons. Okay. And now let's go over the hexahedrons. Okay. All right, so first point. First point is that it can be difficult to mesh geometries with, lots of curvature and lots of complexities. Right. And so remember, the reason for that is because hexes, they look like a box, and so they like to mesh other box geometries. But for the geometries where it does work, it's a lot more flexible in terms of its distortion, right? And so this ends up being that when in the cases where hexes do work, you end up with a much more efficient mesh. Remember, the reason for this is because they can be distorted more than their tet counterparts. Okay. And so if you have a solid with a lot of a geometry with a lot of straight surfaces and sharp corners, hexes are going to do great. But if there's a lot of curvature, you're probably going to end up having to use tets for that. Okay. And so next, let's go over shear locking. And so linear hexahedrons are still susceptible to shear locking because we have those linear shape functions. Okay. Whereas quadratic hexes, we don't have that issue. And finally, let's talk about what it's good for. And so just like its linear tetrahedral counterpart, linear hexes are good for thermal and fluids. Okay. Whereas the quadratic hex, this is good for thermal, fluids, and structures. And then finally, let's talk about, let's kind of remind ourselves how many nodes that we have per element. And so for the linear quadrilateral or linear hex, I guess this is just for the linear hexahedral, we have 8 nodes per element. Okay. And for the quadratic hex, we have 20 nodes per element. All right. And so that's a really big increase. And so if you're going to use a quadratic hex, just kind of be aware of that, you know, especially when you're looking at kind of the cost for your simulations. Okay. Okay. And so this is a table for you, and you know this is actually a little bit nicer quality than the one in the notes, because the one in the notes is not color coded like this, and so you know this is nice. And so if you're when you're trying to decide, you know, which element type to use for your finite element simulation, you know, you can refer to this table to kind of help you make that decision. Right? But just like we talked about before, you know, there's no kind of this is not kind of a black or white thing, and so there's you know, you can make certain elements work in almost any situation, right? It's just you kind of have to be aware of, you know, the properties and what it takes to make it work. And so, you know, just as kind of example, you know, I've you know, for my own work, I've literally used linear tetrahedrons for everything, right? And you know, that's mostly, you know, that's part of the reasons because I don't really work with structural finite elements in my research. But the other reason is, you know, you can make linear tets work, you know, for almost any kind of situation. It's just you know, I'm always kind of aware that, you know, whenever I'm using these linear tets, I have to really give it a really good mesh refinement in order to really get it to work really well and to give me the accuracy that I really want. Okay. And so kind of like what we talked about before, that, you know, when you use a quadratic element, yes, you're paying a little bit more per element, but then you don't need as many elements in order to get an accurate solution, right? But there's kind of 2 paths for that. And so you can either do you could either increase the element order, or you can just refine the mesh, and you know, both will result in more accuracy. Okay. But hopefully, you know, this table kind of gives you you know, some hints about, you know, what situations you would use when and how you would kind of make these elements work for you. Okay. All right. So any questions on this?
So it occurs to me, like, why can tetrahedrons not be distorted with quadrilaterals can? Because like the tetrahedrons are basically just half of the hexahedron, right? Can
Yep.
like.
Yep. That's one way to think about it. Yep. And so the triangles and the tets, you can almost think of as like half of their counterparts. And so that's kind of the reason why that, you know, they're a little bit more difficult to distort. Mm-hmm. Right. All right. So actually, let me write that point down again. So just because it's it's an important one. Okay. All right. Oops. So even though quadratic elements have more okay. All right, so just as kind of a very simple example here. So let's say that, you know, you're doing a simulation on a cantilever beam, right? And so, you know, we have our little beam right here, right? It looks like just a rectangle, okay? So let me draw 2 right here, okay? And so, you know, if you want to reach a good amount of accuracy with linear finite elements, you know, you might have to do a mesh that kind of looks like this. Right, so you have kind of like a little, like a wafer cookie going on here on the left-hand side, right? And so, maybe you did a mesh convergence test and, this is the mesh density that you need for accuracy, right? But if you use quadratic elements, you might achieve the same level of accuracy with a mesh that might look like this, right? And so this is kind of an extreme example. It might not be this different, but this kind of just just to illustrate the point that quadratic elements, you don't have to refine as much, okay? And just kind of keep that in mind. So when you are using quadratic elements, you maybe don't have to have as refined a mesh as before, okay? And in particular, because there's kind of two ways to reach more accuracy. There's kind of a name for that they give it in the industry, okay? And so let's say that you have a situation where you have a mesh, but you want to achieve more accuracy with your finite element simulations, okay? And so there's two routes that you can take that kind of describe this process here, right? And so the first route that you can take is called H-level refinement. And so H-level refinement is basically just making your elements smaller, and so that you end up with more elements in your mesh. And so that's kind of what the H stands for. And so the H, if you kind of remember, when we were doing our ANSYS activities, one thing I have you guys modify all the time is the size of the elements, right? And so remember whenever we make a mesh, I make you guys do a mesh sizing object, and I make you choose the size, right? And so H is typically the symbol that they give for that element size, right? And so if you're reading kind of a technical report on finite elements and they talk about H-level refinement, all they really mean is that they just made the elements smaller, and they use that to achieve more accuracy. Okay. All right. And so the other type of refinement that you can do is called P refinement, or P-level refinement. And so the P in P-level refinement stands for polynomial, right? And so when you refine the polynomial, what they really mean by that is you're increasing the order of the element in order to achieve more accuracy. And so you're keeping the size of the elements all the same. It's just that you're making the shape functions a higher order in order to achieve more accuracy. Okay. Okay. In terms of ease, H-level refinement is often a lot easier to do because all it is is you just change a setting to go from one element size to another one. And so P-level refinement is easy as far as your software can take you, right? And so like we've kind of seen in ANSYS that when we're using ANSYS, we can either do a linear type element or a quadratic one. And so other type elements also exist. And so there's cubic elements, there's fourth order elements, and so on and so forth. But those options, obviously aren't available to you in ANSYS. And so, if you want to continue doing P-level refinement, you actually have to go in and actually implement them in code, which is not a trivial thing to do. Right? But typically when you do P-level refinement, not only do you pick up more accuracy, but you also pick up a lot of other really nice properties too. And so one example for that is the shear locking. When we go from linear to quadratic, the shear locking all of a sudden is just not an issue anymore, right? And so usually, even though it's a lot of work, when you go from one polynomial order higher, you pick up, in addition to accuracy, you pick up a lot of other nice qualities that you would want in your finite element mesh. Okay. But it's difficult. But it's difficult to do. All right. So any final questions before we wrap up for today? All right. So that's all we got time for today. So thank you guys for tuning in. And so Thursday we have another set of notes to do. There's actually a little bit here left that we'll finish up on Thursday, right? And so hope you guys enjoy the rest of your day. And I'll see you guys on Thursday.
One quick question.
Sure.
The homework is due Friday, right?
Correct. Yeah, homework's due Friday.
Is there a way we can get an extension just a little bit?
Yeah, sure. I don't mind because this is the homework that's going to be preparing you for the next midterm, and I don't have another homework planned for that. And so I think this is the last homework for the class, and so everything beyond here will be ANSYS activities. And so yeah, I don't mind extending that to the middle of the next week. Yeah.
Okay, thank you.
Yep. Okay. So I'll change that. And so do you think Wednesday of next week is okay?
Oh yeah.
Okay. Okay. So I'll go ahead and I'll change that on the Canvas site. And so next homework's due next Wednesday.
Okay.
Yeah.
Thank you.
Mm-hmm.
Have a good day.
Thanks. You too.
So you said this was the last homework for the whole semester?
For this class, yeah. So we'll still have our ANSYS activities, and so you'll still have to do that. But in terms of like pen and paper, homeworks like that, this is going to be the last one.
And
So-
the exam, oh, I'm sorry, you can go
No,
ahead.
go ahead. Go ahead. I'm interrupting. I'm sorry.
Oh, no worries. So for exam 2, that one homework would be pretty much what covers or what's covered on the exam?
Yeah. And so the next exam, the focus is going to be on strong form, weak forms, and finite element forms. And so that homework basically covers everything for that.
Okay, sounds good. Thank you.
Yep. Mm-hmm.
I'm slightly confused on last homework. My schedule says we have up to 8 homework assignments.
So that includes the ANSYS activities.
Oh. Okay. Because
Yes.
I have the ANSYS activities and the homework assignments as being separate issues.
Okay, I count them the same. So I when I say homeworks, I mean like kind of take home stuff you have to do outside the class. Yeah.
Okay. So the rest is going to be ANSYS.
Yes.
Okay. So this is the last regular homework
Correct.
except for ANSYS.
Correct. Yeah.
Okay.
Mhm.
Okay. Thank you.
Yep. Mm-hmm.
Awesome. Thank you so much, everyone.
Professor,
Yep. What's up?
can you, I just wanted to see the objectives again for
Sure.
today.
Mm-hmm.
Perfect, thank you.
All right. Did you guys have any other questions before I hop onto my next lecture? Okay. So have a great day, guys, and I'll see you on Thursday.